Okay, let's move on to nonlinear analysis. So firstly, let's just talk about linear behavior. I mean, this was first sort of described back in the several hundred years ago, back in the 1600s by a guy called Robert Hooke, who discovered that structures behave linearly with respect to applying a force. So if you apply a force, the displacement is linear. And that constant of that linear relationship we call the stiffness of the structure. And most, I guess it's true that certainly for a small amount of loading, most structures obey Hooke's law. They have a linear relationship with respect to force and displacement. A common example, is a spring. You apply a load, it deforms, and then you remove the load, and it goes back to its original shape, and it deforms proportionally with respect to the load that you're applying. Now, linear type structures are very well suited for doing finite element analysis. And the reason being is that we only have to calculate the stiffness once, and then we can calculate the behavior of the structure in terms of deformation applied to a particular loading. So it means in terms of doing a linear analysis in codes like Ansys is very computationally efficient because you only have to do this, calculate this stiffness of the structure once. Unfortunately, in the real world, many structures don't behave in a linear manner. They're what we call non-linear. So the stiffness changes depending on the amount of load or the deformation that takes place within the structure. The stiffness is no longer constant, and the stiffness changes depending where the displacement is, and the stiffness at that point of the force displacement relationship we call the tangent stiffness. Okay, so what are these scenarios where we have nonlinear behavior in the structure? Well, there are three areas really. The first one is when the strains, and if we think about metals in particular, where the strains in that metal go beyond the elastic limit. So we can see on the right-hand side there an image of metal forming. We're forming chain links here, and part of that metal forming process is to strain the material beyond the elastic limit to have a permanent deformation which forms the chain links. The next area where we introduce non-linearities into the analysis is when the deflections of the structure become large. So if they're small, it's usually not a problem. But as they become larger, the load displacement changes, the stiffness of the structure can change depending on various phenomena. And if we think about the classic example, the image on the right, the guy with the fishing rod, when you have a fishing rod in its horizontal position, you can apply a small amount of load to the tip and you get quite a large deflection. But when it gets into its vertical position, it deforms quite a long way. It becomes quite a stiff structure, and you need much more load in order to deform that structure. And we can see in the animation there that the load's so high, it pulls the guy off the side of the boat. The third area that we most commonly come into non-linearities when we're doing finite element analysis is contact. So many of the models that you are working on will be assembly models. There'll be contact between the various components. And when parts of that assembly come in and out of contact with each other, there's a change in status. So when they're in contact, there's stiffness. When they're not in contact, there is no stiffness. So that's what we call a change in status, non-linearity. The animation just on the right-hand side that you can see originally had a crash test dummy in slow motion hitting a concrete wall, but I thought the animation of a transit van hitting a roundabout was a little bit more interesting. Okay, what are the implications of doing a nonlinear analysis? When you're doing an FE analysis, what are the implications of introducing nonlinearities? Well, in order to solve the stiffness, we have to do it in sort of a piecewise manner. We have to do it in iterations. So essentially, codes like Ansys will try and solve that solution in iterations. So it'll calculate a force displacement. It will look at the external forces in the structure and the internal forces in the structure, and see if they're in balance. And if they're not in balance, then it does another iteration, it'll do another iteration, until the external forces and internal forces are in balance, and we say the structure is the equilibrium. What that means is a nonlinear analysis has to solve the stiffness matrix multiple times. In this example on the right-hand side, we've solved the stiffness matrix 4 times in order to achieve an equilibrium iteration. So the first thing we need to note from a nonlinear analysis, it's computationally more expensive. Okay, as I just mentioned, we have this idea of convergence where the forces are in balance. Actually, the forces never get truly in balance. They're in balance to within an acceptable limit. We calculate the residual forces. Those residual forces, if they're small enough and they're within an acceptable limit, then we'd say the solution is converged and the solution is in equilibrium. Convergence cannot always be achieved, and this is the second biggest problem with doing nonlinear analysis. The first one is computationally expensive, and the second one is you don't always get a solution. So essentially, Ansys, initially when it first starts, and codes like Ansys, when you're doing a nonlinear FE analysis, when it first starts the solution, it's making a stab of where it thinks the solution is, the initial stiffness, and it iterates to the solution. Now, in order to ensure that you achieve convergence, you have to basically move the force displacement curve in small intervals. You have to start the solution what we call the radius of convergence. And as a user, you don't know how big that radius of convergence is or where it is. So there are a couple of techniques that can help you solve nonlinear analyses. So the first one of these techniques is you have to move up this force displacement curve slowly. So you nearly always in a nonlinear analysis apply the load in small steps. We have the concept of load steps, substeps, and equilibrium iterations. So a load step, generally speaking, is the final load that you want to apply to the structure. So you might take a structure through various different load steps and loading conditions, and the load step is the final load for each of those conditions. You apply that final load in a series of substeps. So let's say we want to apply 1,000 newtons to a structure. We might say, let's apply this in 10 substeps, 100 newtons at a time. So we can define 10 substeps, and Ansys by default will ramp that load on at 100 newtons at a time. So again, in terms of computational, being computationally expensive, instead of applying the load in one load step, we're applying it in 10 load steps in this example. And then for each load step, Ansys has to go through this Newton-Raphson method in order to find the equilibrium. That's at each substep, which may take 1 iteration, it may take 25 iterations, it may take 50 iterations. So as soon as you start doing nonlinear analysis, you have the concept of load steps, substeps, and equilibrium iterations, and you're multiplying the number of times that Ansys has to calculate the stiffness of the structure. So computationally expense goes up hugely once you start doing nonlinear analysis. The second way you can achieve convergence, Ansys has a lot of tools, line search, tools that dictate how Ansys tries to establish the next starting point for each equilibrium iteration. Stability controls, things like putting artificial energy into the structure to make it more stable. There's a lot of controls for contact. We'll cover some of them today. How you monitor, how you manage contact, the contact algorithms, how you detect contact. They can all help you achieve convergence. And the last one mentioned there, convergence criteria. The criteria, these Newton-Raphson residuals, the tolerance that you apply in terms of achieving convergence. Actually, I don't recommend changing the convergence criteria. Ansys puts a default value on there, and usually this is pretty good. You don't really want to be loosening that tolerance and getting a less accurate solution. So let's look at the first type of those nonlinearities, nonlinear geometry. So this is, from the 3 types I mentioned before, the guy with the fishing rod. So Actually, and this is one of the easiest to activate. So if today you're just doing linear analysis and you want to start doing non-linear analysis, large deflection, actually there's only one toggle in Ansys to switch on large deflection. It's under the analysis settings branch, and you select large deflection on. Once you've switched large deflection on, Ansys will take into account large deflections in the structure, so the changing of the stiffness matrix direction as the structure deforms, a large rotation. It will also take into account large strain, stress stiffening, and spin softening effects. So large deflection, which is the most common types of non-linearities introduced by having non-linear geometry. It's where the element's orientation changes as the structure changes. So it's local stiffness and global stiffness, depends on the actual deformation at that point in time. Yeah, at this point, I want to just run into a quick demo. So what we're going to do here, if I start Ansys, I open up Ansys. What I'm going to do is firstly just a structural analysis, a linear structural analysis, should I say. So I'm just going to import some geometry here. We're going to look at the three types of non-linear behavior and see what difference it makes in terms of the results of this particular structure in terms of the results. So to compare, we have to do a linear analysis to start with. So let's open Ansys. So Ansys is just starting. I always find when I'm doing demos, it says down at the bottom left-hand corner, starting mechanical. For those of you that are not familiar with Ansys, what you can see on the screen at the moment is the project overview. We call it Ansys Workbench. I've started a structural static analysis, and then I'm just starting the Ansys mechanical application to start processing that simulation. So what you can see now is the Ansys mechanical application. And I've brought in, I mean, this is typical of a lot of types of geometries we see that customers are using. Mostly today, customers are building geometry in CAD. Those CAD models are made up of multiple parts, and you have an assembly, as we can see here. So we've got a bracket assembly. What I'm going to do here is just fix this base. I'm going to apply a bolt pretension on here to compress this upper bracket. So the first thing I want to do here is just put a mesh on this model. So I'm going to go down to the mesh, and I'm going to set the element size at 2 millimeters. I'm also going to put a mesh control object in here. So I'm going to insert a sizing control. And actually the base of this bracket, I'm not too interested in. It's just there to support the model as part of the model. So these components here, not the washer and the lower bracket, I'm going to apply a larger mesh size on. The solution there, I'm less interested in the accuracy. So let's have a look at that mesh, generate the mesh. Oops, one other thing I wanted to do was set this to, actually one of the other things I need to do is set the units to millimeters. That would be good. Put the right size in. Just to show you that I'm doing this live. Let's regenerate that mesh. Actually, now that's looking a lot better. So we're now working in millimeters rather than meters. And now I can go down and apply some boundary conditions. I'm going to insert a fixed support, and I'll fix the base of this lower bracket. And then let's just switch the mesh off, and I'm going to insert a bolt pretension on this bolt. And I'm going to set the preload on this bolt pretension as 10,000 newtons. Now, lastly, I'm going to insert deformation total of some result items. So I'm going to insert deformation, stress, equivalent stress. Actually, this equivalent stress, I'm interested in what's going on in this upper bracket. So I'm going to apply it to the upper bracket. And I'm going to insert a deformation, sorry, a probe, deformation probe. I'm interested in how far this deforms. So I'm going to put a probe which will plot the deformation at this point. And the direction, if we, is the vertical direction in this case is the minus x direction. So now I'm ready to do, this would be a linear static analysis. So at the moment I haven't introduced any nonlinear into this analysis. The contact is all bonded, the materials are all linear, there's large deformation is off. So I could solve this. Because I'm going to copy this analysis and compare the difference with the nonlinear analysis, I am going to put some time stepping into this. So strictly this isn't required for linear analysis, but I'm going to add it just so we get a nice graph and we can compare this with the nonlinear analysis. So I'm going to ask Ansys to solve this in 10 substeps. So it will increment this 10,000 Newton load in 1,000 Newton increments. Yeah, if I've got everything right, I think we're ready to solve there. So we'll do so. So the solution is solving. For those of you who are not on the latest version of Ansys, the progress window that you typically see in Ansys has been moved down on the latest version down to the left, down to the status bar at the bottom of the left-hand side. So we can see as the solution, it's nearly there, solution at 100%. And we've got some results. So if we look at the deformation, around about 6 millimeters in this case, equivalent stress, and we've got some result deformation versus time. Because we loaded this, the 10,000 newtons over 1 second, the time is a pseudo time. 0.1 is 10% of the load, 0.2 is 20% of the load, and so on and so forth. So let's just grab this, put this into an Excel spreadsheet. So here we have our linear results. And let's chart those. So if we do insert the chart, let's make that a little bit bigger. And here we can see the displacement versus load. And by inspection, we can see that is a linear. So let's go back to our analysis. Actually, what I'm going to do is just close this first window. We'll do it as a nice project. I'll duplicate this whole analysis. When I've duplicated the whole analysis, I'll reload it and switch on non-linear geometry. So again, on the left-hand side here, Workbench is telling us it's busy. It's just copying that project at the moment. Should take only a few seconds. Okay, so let's start this second. We'll rename it. So again, we started mechanical. Should only take a few seconds. Okay, so we've got exactly the same model, and as I mentioned in the presentation, to switch on nonlinear geometry, the only thing we need to do is here where it says nonlinear geometry in the bottom left-hand window, is change this to on, and we're ready to go. So I'll click solve. And now we're doing a nonlinear analysis. When you're doing a nonlinear analysis, it's worthwhile watching the solution information. So I can go down here, and we can plot these the force convergence. So these are the difference between the criterion we're trying to achieve and the actual forces in the system. So straight away, we've switched on nonlinear geometry. I can see for this first substep, it's taken 2 equilibrium iterations. So here we're looking for the purple line to drop below the criterion, which is the cyan colored line. So initially it took 2 equilibrium iterations, and then for each of the subsequent substeps, it's taking 1 equilibrium iteration. Down here, if we look at time, we can see that we're 60% through the simulation, the time steps, 70%. Full load is applied at 1 second, 80%, 90%. And the solution is completed. So here we've got some results. Now, the first thing I can see, I don't know if you noted, I didn't particularly point out, but the deflection in the linear example was 5.9 maximum. Now it's 6.6. So by adding in nonlinear geometry, we've got a different result, essentially. Let's have a look how different. So if we look at this deformation probe, copy the results. I'll insert these down here. And let's compare the two graphs. So if I do select data, add, the data. Okay, and we can see the difference between the two results. Actually, even though we've got nonlinear geometry on, the orange line, which is the nonlinear, let's just put on the legend so we can actually see which is which. So the nonlinear analysis, we can see we've got a different result. It's the orange line. It looks fairly linear, but there's maybe a slight curve in there due to the nonlinear behavior of the geometric structure. So you can see straight away, introducing nonlinear geometry, it took more equilibrium iterations to solve. It solved quite easily, but we got a significant difference in results. So let's just go back. I'll duplicate this model ready for the next demo. And let's jump back into the presentation. So the second common area we see when users need to use non-linearities in the model is contact. So when you, well, let's look at the definition of contact to start with. So the definition of contact is when two surfaces touch each other, they become mutually tangent. And it has the following characteristics. They do not interpenetrate. Physically, they don't pass through each other. They transmit compressive forces, but normally not, compressive forces and tangential friction forces when they're sliding, but they usually don't transmit tensile forces. So as you pull the components apart, a gap opens up and there's no tensile forces. So surfaces are usually free to move away from each other. Contact is a change in status nonlinearity, and those sort of change in status nonlinearities cause problems for numerical methods. You know, when a step change in something is always a problem. But essentially, when something moves in and out of contact, it's either got stiffness or hasn't got stiffness. So Ansys has to handle that internally. In Ansys, there were 5 types of contact. So when you bring in some geometry, as we saw with the bracket, Ansys automatically creates contact pairs between coincident surfaces from different components, or surfaces that within a given tolerance from different components. And it always applies bonded contact to those surfaces. So by default, parts in an assembly will behave as though they're bonded, welded together, glued together, whatever term you want to use. Bonded is a linear contact, and it means that parts cannot move apart and they cannot slide relative to each other. No separation is also a linear contact, but parts can slide in no separation, but as it describes, they cannot move in and out of contact. The latter 3 cases, rough, frictionless, and frictional, are what we call nonlinear contact cases. So these are all types of contact where the parts can move in and out of contact. So rough allows parts to move, to separate from each other, but they can't slide. If they are in contact, they don't slide relative to each other. Frictionless contact allows parts to both move in and out of contact and slide relative to each other. And frictional is a little bit as it sounds, is like frictionless contact, but if they are sliding, you can define a friction coefficient. So there's some shear forces or frictional forces applied when the two parts are sliding relative to each other. Rough, frictionless, and frictional are nonlinear analyses. So if you include this in your simulation, you're going to have that computational overhead that comes with nonlinear analyses. So wherever possible, try and get away with bonded or no separation analysis. Your analyses will run much faster. Also, for those of you that have tried playing around with contact, there are different formulations. So there's what we call augmented Lagrange. This is the default in Ansys, and it's a type of penalty method. We also have pure penalty. So the first two, pure penalty and augmented Lagrange, are what we call penalty method contact types. These are nonlinear contact types, allow the structure to move in and out of contact. There is a third nonlinear contact type called normal Lagrange. Normal Lagrange will give you very accurate, it allows, so just moving back, the penalty methods, the first two, allow a small amount of penetration between the two parts. And that penetration, the amount of penetration is controlled by various settings. It makes them computational. It's fairly computationally robust. They should converge reasonably well. Normal Lagrange is a method that doesn't allow penetration between parts, so it's good for when you want highly accurate results on surfaces of mating parts, but it does suffer from convergence problems. You're going to have a lot more equilibrium iterations or struggle to get convergence using normal Lagrange. MPC and beam methods are linear methods, so if you've got bonded contact, you can use these methods. Augmented Lagrange is the default method, and for most assembly models, I would recommend sticking with augmented Lagrange. It works quite well, it's reasonably robust. Some of the other settings you can check in Ansys when you've got a contact pair and can affect nonlinear behavior is the detection method. By default, Ansys will create what's called a contact and target surface, and in the normal behavior, the contact surface cannot penetrate the target surface. The detection method is at Gauss point, so Gauss points from the contact surface by default cannot penetrate the target surface. There's what's called a penetration tolerance when you're using these penalty methods, and essentially the way it works, if you look at the graphic on the right hand side, when a contact surface penetrates a target surface, effectively some stiffness is applied, springs are applied. It doesn't apply spring elements internally, but a stiffness is applied to oppose that penetration. And the stiffness of that spring and the amount of penetration is dictated by the penetration tolerance that is set and the penalty stiffness that is set on the contact control. Normally in Ansys by default, you leave Ansys to set these values, and they're usually pretty good. But occasionally, maybe 90–95% of the time, they're good. 5–10% of the time, you may want to override the values that Ansys use. The other thing that can control convergence is pinball radius. So pinball radius is basically a measure of the proximity from the contact surface that Ansys looks for the target surface. If the pinball radius is big, then it will include more of the contact points, and it can affect this solution time. So again, that needs to be chosen appropriate. Again, the best advice is to use the program controlled. There's a point there that I've highlighted in bold. The penalty stiffness is your best friend. So of those of you out there that are doing contact analysis using the standard methods and you're struggling with convergence, relaxing or increasing the penalty stiffness is your best friend in terms of convergence. As a general rule, lowering the penalty stiffness will improve convergence, but only if you're not exceeding the penetration tolerance. So there is a trade-off. So let's have a look how nonlinear contact can affect our bracket simulation. So if we go down here, I copied the original simulation. Let's add in nonlinear contact in this example and see how it affects the results. So let's open this model. So Ansys is just starting, mechanical application is just starting. So here we've got our model again, and we didn't look at the contact in the original analysis, but if we go down onto this connections branch here and contacts, you can see I've got 11 contact regions. These were automatically created when I imported the geometry by Ansys based on the proximity of the surfaces from the different parts. One thing I always do when I go in, and I think this should be default really, but that's just my view, is rename based on geometry. So quickly I can see the contact type and I can see which parts are mating. So what I'm going to do in this simulation is I'm going to allow the upper face of the bracket to open up with respect to that upper washer. So if I select the contact which represents the upper bracket to top washer, we can see here, I'm going to change the bond type of contact from bonded to frictionless. Also, there is one, if I want it to open up, I also need to change the contact between the bracket and the shaft of the bolt as well, or else it doesn't make sense. So I'll change that to frictionless as well. And I've changed that contact type, and now I'm ready to solve. So I'll go down, select solve and set the solution going. And then we'll plot the force convergence curve as the solution continues. Now, straight away, you know, the first iteration we can see, and this is typical actually, we see this in a lot of customers that are doing structural analysis with large assemblies. The first load step typically takes a long time to converge. Ansys is trying to establish that contact between in this case, the top washer and the bracket. And initially it struggles to achieve convergence. So we can see the purple, which is the calculated forces. There's quite a lot of difference between the residual forces and the criteria. It does, if I've set this up properly and haven't changed anything from my test runs, it should converge on 21 equilibrium iterations. We can see it's coming down slowly. And there are some of the techniques, softening the penalty stiffness, for instance, would make this converge a little bit quicker. And there are some other techniques that can help convergence. You can see actually the first substep was converged after 21 equilibrium iterations. So that's 21 solves of the stiffness matrix. So as opposed to a linear analysis, we'll do the whole load case in one equilibrium iteration. So again, we can see non-linear analysis, including non-linear contact, if it's not needed, can add to the computational effort of the analysis. Obviously, if you want accurate solutions, sometimes you can't avoid non-linear contact. So we're currently at 32% of the result. Looking at the time, it's 0.325. The final load is 1 second, so at 32%, 42%. And we can see actually, so far, it's using several equilibrium iterations for most of the time steps. Actually, I know from my test run through on this, the last few times substeps, it solves with just one equilibrium iteration. And that's because the structures, the contact isn't changing as the structure moves through the last sort of 40–50% of the loading. Okay, we've got a solution. Okay, so if we look at this solution, we just look at the deformation plot. We can see here that there's a gap opened up between that washer. What this has actually meant is that the load that's applied to the bracket is at the back face of this washer, which means you've got sort of a moment on that load, which has actually meant that the deflection at this tip is much higher. It's gone down to 12 millimeters. So from 6 millimeters down to 12 millimeters. Let's have a look at that in our graph. So if we do our deflection probe, select the data, copy it and paste it into our Excel spreadsheet. nonlinear contact. Let's have a look. Select data, add. For those of you out there that are Excel wizards, there may be a better way of doing this, but this is the only way I know. Okay, so now we can start seeing this huge difference between using the correct contact in this case and the incorrect contact. 12 millimeters deflection on that tip as opposed to 6 millimeters. The other thing we can sort of see, and I don't know if it comes out okay over the graphics, is that this grey line, which is the nonlinear contact, particularly at the beginning, there's a slight curve in here. So again, it's no longer purely linear. There is nonlinear behavior in terms of the deflection in relation to the force. Okay, let's jump back and look at nonlinear materials, and I'll just duplicate this again in readiness for the next part of the demo. So let's just go back to the presentation, discuss nonlinear materials. Nonlinear materials is a big subject in itself, as is nonlinear contact. Actually, EDRMedeso and Ansys do run a 2-day training course on advanced contact. And similarly, we have a number of training courses on material and different material behaviors. So I'm going to concentrate today just on nonlinear material behavior, more metal for metals. And actually 90%, I don't know the exact percentage, but approximately around 90% of customers are working within the linear range of materials. So if you imagine working with steel, for instance, or other engineering materials, they have this elastic range. Below the yield point of the material behaves in almost an elastic manner. This is due to the ionic bonding being stretched between the different molecules in the metal, and then as you release them, they just go back, and they obey Hooke's law. If you apply a load that's too high, those ionic bonds break, and you get what's called a dislocation in the metal. And when you release the load, that dislocation doesn't go back. And as you apply loads, you get an increase in dislocations, and dislocations stop more dislocations, and the structure becomes harder. So a typical stress-strain relationship for metal, once it goes beyond yield point, is something as we can see in the graphic on the right-hand side. So if you're not interested in what happens after yield, you can use linear materials. They work quite well. For most engineering applications, you're not wanting to yield the material beyond the yield point, and you're not interested in plasticity. But there's a lot of applications that Ansys has applied to where you are interested in the plasticity. So for instance, if you wanted to model the metal forming of those chain links we saw in the graphics earlier on, you know, you wanted to model a metal forming process, or maybe you're happy to have a certain amount of plasticity in your model for whatever, in your structure for whatever reason, maybe to absorb energy, then you might want to model metal plasticity. So plastic behavior can be described as elastic or perfectly plastic. So that assumes perfectly plastic assumes there's no hardening after the there is no hardening after you pass the yield point, or you may have strain hardening. It can also be rate independent or rate dependent. So generally at low temperatures, metals are rate independent. The amount of plasticity isn't dependent on how quickly you apply the load. You know, when some materials, viscoelastic, for instance, they have a relationship to how quickly the load is applied, and metals, when they're at high temperature, can become rate dependent. You also have this thing called a flow rule. So this is which way the strains develop depending on an applied load. And some materials are what we call associative. So the strains develop in a direction which is normal to the yield. So typical engineering metals behave in this way, or non-associative. So cast iron and other concretes use different types of models where the strain can develop along a different plane. You also have the concept of hardening, and most metals exhibit what we call either kinematic hardening or isotropic hardening. So small strain, generally kinematic hardening, isotropic hardening for large strain. And these models or these rules dictate how the metal behaves once you've strained it into the plastic region, and then you cycle the load from tensile to compressive loading. Just as a quick description, with kinematic hardening, if you tensile load the material in the tensile direction, the yield point will move in space. So the compressive yield point will reduce in proportion to the tensile yield point. When you're using isotropic hardening and you strain the material in the tensile direction, the actual yield point gets larger in the compressive direction. So the yield surface increases in size instead of moves in space. Okay, assigning nonlinear materials in Ansys, you basically assign a nonlinear material model. Typically for metals, you apply a stress. Apply a stress strain curve. It can come in two forms: a bilinear stress strain curve, which is quite simple. You have a Young's modulus and then a tangent modulus, and you assign a yield point, or you can apply a stress strain relationship in a table, and you get what's called a multilinear stress strain curve. Stress strain should be true engineering stress strain. In Ansys, there is a rich library of nonlinear materials. We're not going to cover them today. Nonlinear models and algorithms. Anisotropic plastics is mentioned here. Rubbers we come across a lot. Rubbers are in what we call non-compressible or nearly non-compressible materials. Can suffer from a lot of problems and a lot of controls to help convergence. Cast iron mentioned, masonry, shape memory alloys, viscoelasticity, lots of different material models. And as I said previously, Ansys has a lot of training material and training courses on advanced material modeling. So let's look at a demo. Let's introduce metal plasticity into our demo. So I'll go down and we'll rename this model. Nonlinear materials. So the first thing I need to do actually is edit the material. So we'll edit the material data sheet. I'll copy. So far we've been using what's called structural steel. I'll just make a copy of this structural steel. We'll call it nonlinear steel. And I'll add this bilinear isotropic hardening model. So down here, it's asking me for the yield strength. So I'll put U.2.5 E to the 8. And then tangent modulus 2.0 E to the 10 I'll use. And we can see what that looks like. So I'm applying a bilinear stress strain curve to this material. So if I go down and open this model, now it's saying upstream data needs to be reread. So I've changed the material model, or I've added a material model, so it's going to import that when I start the analysis, or start the mechanical application, should I say. Okay, so here we've got a copy of our linear analysis again. To include nonlinear materials in this, we have to apply this nonlinear material model. So I'm going to apply it to this bracket, the bracket that we're interested in. So if I select the upper bracket from the tree, you can see it highlighted in green, and I go down and I select nonlinear steel, it will now apply this nonlinear material to that bracket, and I'm ready to go again. So let's just click solve. And let's see how the convergence works for this particular model. select force convergence. So initially it solves quite easily. The first sub-step, one equilibrium iteration. Second one's taking a little bit longer. If we keep our eye on the time here, we can see how it's progressing. 30% of the load, 40%. We can see it's taking typically 3 equilibrium iterations for each of the load steps. So again, by introducing nonlinear material, it's becoming more computationally expensive. %, there. And the solution's completed. So let's have a look at the deformation. So here we can see the deformation is now 27 millimeters. If we go to the results branch, actually this, I advise everybody doing this for nonlinear analysis. If we look at the true scale, Ansys by default will scale the plot so it looks less than it is. Quite often it will display it so it's more than it is. For nonlinear analysis, if you want to see exactly what's going on, then you should select the true scale. And here we can see it's compressing quite large, quite highly. Let's have a look. We might want to, at this stage, look at the actual strain. So let's have a look. Put strain and select equivalent plastic strain. Evaluate results. We can see where the strain's occurring. Let's have a look and plot the force deformation curve. So again, I'll grab these values from the deformation probe, insert them into our spreadsheet. Add them to our chart. And here we can see the sort of extreme. So with non-linear material, initially before it starts to yield, it follows the linear load displacement path. But once it starts to yield, you can see it change significantly. And the result we get from using non-linear materials, because we're taking this bracket well beyond the yield point, the strain is quite high. So I hope that shows how you introduce the different non-linearities into your model and the effect they can have in terms of run times, the effect they can have in terms of results. So it really is an engineering decision on what you include. Just a general rule of thumb is try to keep the analysis linear where possible. So for instance, if you think you're not interested in having opening and closing on these washers as I have here, then leave it as bonded contact. Don't switch on nonlinear geometry unless you know or suspect it makes a big difference in the results. Always try and keep your analysis linear to keep your run times and computational overhead down. Okay, so what I want to do now, and I might run over the allotted 1 hour here. If we just go back to the presentation, I've got a couple of other topics related to nonlinear and a couple of demos that I'd like to run through. The first one is nonlinear buckling. So buckling is a phenomenon that occurs in a structure where you get a sudden collapse in the structure. The stiffness of the structure suddenly goes down to 0 and you get a sudden collapse. We all know this. We probably did, as kids, we probably took an empty Coke can, stood on it and pushed fingers in the side and the thing collapsed. We're all familiar with this type of problem, and structures fail from buckling out there in the field. We can see on the right-hand side, a wind turbine that's collapsed, and we can see a model of that. So just to reiterate, for nonlinear buckling problems, they're characterized by having, in the load displacement curve, having a point where the stiffness becomes 0. And numerical methods really struggle when the stiffness becomes 0. The point at which the stiffness becomes 0, there is a theoretical limit, a buckling limit. In fact, a guy called Euler came up with a set of equations that would allow you to calculate the buckling load numerically. And we can do this. The technique is called an eigenvalue buckling analysis, and it will calculate the theoretical limit. The other method is using a non-linear analysis and actually applying the load and modeling the buckling behavior, including the post-buckling behavior. We're going to cover that today. Both these methods give a non-conservative result. And the reason being is that actually in the modeling world, if you imagine taking a tube and applying a load vertically, as we can see on the right side, normally in the modeling world, that tube is perfect. It's perfectly shaped, it has perfect geometry, there's no corrosion, there's no imperfections in the material model. So normally it gives you a perfect buckling load. In the real world, things like non-perfect geometry, corrosion, any imperfections in the model perturbs the model, and it means that the actual collapse load comes on a little bit earlier. So if you're doing buckling analysis, you need to keep in mind it's non-conservative results that you get, and you need to apply some sort of safety factor. I often see out there in the field users applying a buckling safety factor of 3, so they assume the buckling load is a third of what's being calculated. As I've mentioned before, there are a couple of techniques. Linear eigenvalue buckling, we're not going to discuss today. It's a linear analysis. You can do a linear eigenvalue buckling with non-linearities in the model. It's just a different calculation. You have to calculate the buckling load. But what I want to concentrate today is on non-linear buckling. So non-linear buckling is characterized by collapse of structures, snap-through analysis. So if you imagine, again, I mentioned a Coke can once, but if you have a Coca-Cola can, it has a dome at the bottom. If you increase the pressure inside the can, that dome will snap through. We call that a snap-through analysis. And also, it's also a type of buckling. So, as I mentioned before, at the point buckling occurs, the structure has 0 stiffness. Numerical methods struggle to handle this. And what Ansys does, what you can do in Ansys is you can apply nonlinear stabilization. So this effectively applies some damping terms into the structure to give it a certain amount of stiffness at the point of buckling, which allows you to calculate past that buckling point. Now, you've always got to bear in mind, if you introduce any sort of artificial energy, in this case damping, your result is compromised in terms of accuracy. So you have to make sure it's large enough to get a solution, but small enough not to affect the results. So let's have a look at a demo of nonlinear buckling. So I'm going to put in, again, let's add a structural static analysis in here. And I apologize for those that may have to go at 12 because I'm going to run over here. I'm going to look at explicit dynamics after this, so we may go on to about 12:15. Anyway, this particular example, we're going to bring in a tube and buckle the tube. So let's open the analysis. So again, Ansys taking, and the mechanical application taking a few seconds to open. And here we've got a tube. It's perfect cylindrical tube. It's a half section. So we're going to make use of symmetry in this model. So the first thing I need to do, it's a shell model, so I need to assign, and it's 10 meters in length. I need to assign some thickness. So I'm going to make this tube 50 millimeters thick. And I'm going to assign some symmetry on this. So I'm going to insert a symmetry region. I'm going to select these edges for the symmetry region. These edges lie on the cut plane of this tube. And the symmetry direction, if we look at the triad in the right-hand corner, is in the Y direction. So if we go down here and select Y-axis, that's restrained in symmetry. And then we're going to fix the bottom of this tube. So I'll go down to the tube and insert fixed support. And then I'm going to apply, actually I'm going to do analysis here. Rather than apply an actual load, I'm going to apply a shear load similar to the wind turbine. So if I go in and select insert a force, I'm going to define it using components because it's a shear load, it needs to be in the X direction. And it's quite large, so it's 1 to the 7, so it's 10 kilonewtons I'm applying to this structure. And we're going to look at the deformation. Now, in terms of the analysis, I'm going to set the mesh size to 400 millimeters. In terms of the analysis, so doing this nonlinear buckling analysis, the first thing we need is large deflection needs to be on. And we need to set up some stabilization. So down here under analysis settings, nonlinear controls, set this to constant. And I'm going to put quite a large damping in here. Large damping value in here, help it converge quicker. Now I am ready to go. However, there is one step that I missed out here. For this type of analysis, large deflection needs to be on, and also you usually need nonlinear materials. So I'll just go in and edit my steel, default steel. I'll use the values we saw before. So we'll convert this to a nonlinear material from a linear material. I need to just refresh the materials because I forgot to do that at the beginning. Oops. So structural steel, if I go in here now, we can see we've got my nonlinear curve and it's applied to my parts. So I should be ready to go here if I haven't made a mistake. I'm not confident I haven't, but let's give it a go. Let's press solve and monitor the solution information. So if we look at the force convergence curve, actually it's converging very quickly. It's got up to sort of, I think I have made a mistake in here because it's gone beyond where I expected. Okay, so I'm just going to stop this because the results aren't what I've expected. I'm just going to revisit my settings. So we've got structural steel, which is nonlinear. We've got a symmetry region, which is in the Y direction. The mesh is 400 millimeters. The mesh looks good. The fixed support is good. The force looks good. Let's go down into analysis settings. Large deflection in long. Okay, one of the other things is, and this is the joys of doing a live demo, I mentioned right at the beginning, when you do a nonlinear analysis, you usually do this, you usually set some sort of time steps. So actually, this is the bit I missed out, 100 time steps, 100 time steps and 1000, 1 e to the 7. So, I mean, this is, sorry, 1 e to the 7. Okay, so I'm a little bit confused here. So again, and this is actually typical for nonlinear buckling. I always try and use 100 initial time steps, a minimum 100 time steps. So if it starts to struggle to converge, in this case, it should be around 66%. If it starts struggling to converge at 66%, 66 time step, then we know it's 60, the buckling load is 66% of the applied load. We also need to allow it to automatically bisect the solution to a very small time step to get through that instability point when buckling occurs. So I think I've said that one right. Now let's solve this. And let's see if this looks a little bit more like I expected. Yeah, so initially this looks better. So initially, if we look at the time stepping, it's going up reasonably quickly. We're converging fairly quickly. We can see, if we look at the force residuals, they're starting to build up now, but still okay. Now, in the old days, before Ansys introduced, and I'm talking sort of over 20 years ago, before they introduced stabilization, you did this type of analysis until the solution failed to converge. And at the point it failed to converge, you knew the solution was unstable, and that was your buckling load. I can see now that Ansys has done its first bisection, so it's cutting back the time step. It's done that to enable to overcome this instability, and it's done it at 66 or 0.66 seconds, so it's 66% of the load. And I could at this point stop the analysis, and we've got our buckling load. I'm just going to let it run on a bit, just so we can get some of the post-buckling behavior. And we can see Ansys, actually, if I plot the time interval, time increment, we can see the time increment is quite small, and Ansys keeps increasing it and then keeps having to come back, keeps increasing it and having to come back. So it has to change, it has to apply the load in very small time steps at this point where there's instability. Let's just let it run on a little bit longer. Now, I know this from previous runs. This takes about 800 iterations. We're currently on 290. It takes about 800 iterations to get a full solve. I just want it to run on a little bit longer. I'll stop the solution just to get some of the post-buckling behavior in there. Okay, let's pause the solution there. I'll use the interrupt button. So I'm probably not going to start it again, but it would allow me, if this was my own analysis, to stop, have a look at the behavior and restart it if I want. So if we go to deformation, and we can see there. So here we can see, we've got it on true scale. We can see how it's starting to buckle and collapse down here. And if I started this solution and gone again, it would go on and it would solve to the full load, and we'll get a almost 90 degrees bend in this structure. So that's non-linear buckling, and it's a specific type of analysis. We do see quite a lot of it being done. It's quite computationally expensive, particularly if you want the post-buckling behavior. Okay, I'm running well over time here, but I just want to spend the last sort of few minutes, 10 minutes or so, let's put this back on slideshow, talking about another subset of nonlinear analysis, and this is explicit dynamics. So explicit dynamics is a different type of solver. So far, when we're running in Ansys Mechanical, we're using what's called an implicit solver. But there are different methodologies, a different sort of method, if you like, which is called an explicit solver. And these are used for high-speed, highly nonlinear events. So an implicit solver, such as Ansys Mechanical, it solves the stiffness matrix at each step, and it achieves stability and equilibrium. An explicit solver is an uncoupled solution. It doesn't solve the stiffness matrix, it just solves the mass matrix. The general procedure is this. It calculates the forces at all the nodes from the stressors, boundary conditions, and contact at time t. From the mass matrix, it can then calculate the accelerations. From the accelerations, it does a double integration to come up with a distortion at time t plus 1. And from that distortion, it calculates the stress at time t plus 1, and then it repeats that cycle. It's a very robust solution, very quick at each time step, but it does have a caveat in that the time steps need to be really small. So when do I use an implicit analysis? When do I use an explicit analysis? When time's involved? Well, general rule of thumb, if it's less than 1 second, you use an explicit solver. If it's more than 1 second, you use an implicit solver. And the main reason for that is that an explicit solver, the time step is governed by some physics. So above 1 second, the number of time steps becomes huge and the run times become not practical. So the time step is governed by what's called a current Friedrich-Lewis condition, and this is a function of the element size and the speed of sound in the structure. The time steps tend to be quite small, especially if you're using a high number of elements. What is it typically used for? High energy impacts, so high speed events. Drop testing, as we can see on the right hand side, we're drop testing some pressure vessel. Failure through impact, time-based dynamic response due to something impacting in the time domain, failure and damage footprint, deformation and reaction force studies. So let's just do a quick explicit demo. And I promise this is the last demo and we'll be finishing soon. So if we go back to our worksheet, let's add an explicit analysis. So we're using a different system here. We're using explicit dynamics. Engineering data needs to be nonlinear material. So I'm going to again add this bilinear isotropic model. Those of you who might notice the tangent modulus I put in this model has been a little bit lower. I'm going to import shear plates, start Ansys Mechanical. So in this particular example, actually I put together, I mean, it was some time ago, it was actually a demonstration to show somebody how you use joints in an explicit analysis. But it makes quite a good demo, I think. I'll let you guys be the judge of that. So here we've got 2 plates in the model. They're not connected at the moment. We're going to connect those with joints. And here we've got a slug. So we're going to put a velocity on this slug and hopefully blast through this plate. The first thing, when you're working in explicit, it's best to always work in the metric system. You can set everything up in other systems, but systems of units, but it solves actually in metric. I can see on the right-hand side, because I've got some shell models in here, it's asking for a value. So I'm going to set these plates at 8 millimeters. Mesh size, I'm going to go down and set it 0.01, 10 millimeters. Let's have a look at that mesh. Okay, as I say, mesh is critical to explicit analysis. The mesh size, the smaller element size dictates the time step. next thing I need to do is apply the boundary conditions. Well, actually, the next thing I need to do is join these things together. So let's switch this off, go down to connections, insert a joint. Zoom in here. So I'm going to select these edges and apply a joint to these just to connect them together. And this will apply a spider of MPCs to connect the two parts together. If I duplicate that joint and on the same, let's keep it interesting. Let's just connect two of these holes. Leave the third one unconnected. Also saves time. So I've connected two of those holes with joints. So now we can start applying our boundary conditions. The first thing I need to do is apply an initial velocity to this slug, which is going to impact with the plate. So if I select the part, I'm going to define the value by components. So I'm going to put in 250 meters per second towards the plate. We also need to fix the end of these plates. So if I select this edge, the two out edges of the plate, and we'll insert a fixed support. And then we need to have some analysis settings. So under analysis settings, what's the end time to the solution? So in explicit analysis, it will continue until we get to the end time. I'm just going to set a few other things. So the output controls, it will do hundreds, if not thousands of time steps. So you need to specify when to write the results. So I'm going to write at 50 spaced intervals. And lastly, so it punches through the plate, I can find the settings, erosion controls. Here we define what the strain limit is before and it uses element birth and death. So I'm going to put 0.25 in here. And let's insert deformation and let's insert strain, plastic strain. And I should be ready to go there. I'm rushing along, so let's give it a solve. Let's set the solution going. Okay, straight away we can see if we look at the solver output, it's different from what we might be used to in standard Ansys, and this is because it's using the explicit solver. Nice thing to watch when you do an explicit analysis is the energy summary. So here I can see at the top I've got kinetic energy. It's quite high. This is the slug moving through space. At the bottom I've got contact energy and internal energy. And now we can see the values changing. So now I know the slug is impacted with the plate. We can see the kinetic energy coming down, the contact energy and the internal energy going up. So this is transferring the kinetic energy from the slug into strain energy and contact energy in the structure. There is some hourglass energy. So this hourglass energy really is an error. We want to keep that as minimum, but it is quite small in this case. So I won't let the analysis go through to the full solution, but I'll stop it in a few seconds and we'll have a look at the results. Nearly finished. Should be finished in the next couple of minutes for those of you that have stayed on. So let's just stop the solution there. Let's see what we've got. And actually in explicit analysis, it's quite easy to stop and restart the analysis. And here we can see the slug is just starting to punch through the plate. Let's just animate that result. Also, I think if we zoom in here, we can see the dynamics of the plate as we go through there. Obviously, if I ran this analysis for long enough, we would see the post punch through dynamics of the plate. So one of the other use cases for explicit methods is for time-based, time domain dynamic analysis. Okay, I want to end there. Just as a summary, let's just go back and look at the last slide in the presentation. So in summary, for those of you doing primarily linear analysis, you need to keep in mind that the world is primarily non-linear. So a linear analysis is an assumption. You do need to use your own engineering judgment on whether you should be doing a non-linear analysis or a linear analysis. If you're doing non-linear analysis, you're going to get a more accurate solution, but it's going to take longer. It's going to take longer to run. It's going to be more computational, expensive. And the last point, and this is the sales bit, I guess, Ansys has a full suite of non-linear capabilities to handle most of your requirements, if not all of your requirements. So I'd like to finish there. I'd like to thank you all for attending.